And now we get to the heart of this chapter, which is on the different units of concentration. When we define concentration, that is simply a measurement of how much solute there is in the solution. And there are many different methods that we can use, including several that we're not going to actually learn in this class. But I'm going to start with molarity, which is the most convenient for chemistry. We'll then look at weight volume percent and volume percent. Milliequivalents per liter, which gets used a lot in medical contexts. And then there are other methods which I will not bring up, which we will not study in this class. So we'll start with molarity. So it is by far in chemistry the most common way of measuring the concentration of a solution. You've probably seen this already on different bottles that we've used in the lab videos. The letter M preceded by a number, and that's simply the molarity. So the definition of molarity is the moles of solute for every liter of solution. So, for example, let's say we wanted to prepare a solution which was 1 molar sodium chloride. What you could do is take 1 mole of sodium chloride, and that would be 58.44 grams if we were to measure out the molar mass, and then add enough water to it until the final volume is 1 liter. We don't say add 1 liter of water because the sodium chloride can affect the volume itself. In some cases it will take up some of the volume, and in some cases the attractions of the ions will pull the water molecules closer, and you might need to actually add even more than 1 liter. So we just say add enough water to get the solution to a total volume of 1 liter. On the other hand, if we had a 2 molar sodium chloride solution, that would mean that there's 2 moles of salt in every liter of the solution. So 2 times the molar mass, 58.44 grams. Of course, we don't have to form 1 liter at a time or 2 liters at a time. The molarity is simply a ratio that we can use to figure out how many moles there are in any given volume of solution. So let's go ahead and take a look at a couple example problems where we can make use of the molarity. I'm going to switch over to my notes view. So in this problem, we are given 2.50 liters of our solution of potassium chloride. We would like to make use of the molarity, which will act like a conversion factor. It can be separated into 2 units, moles of potassium chloride for every liter of solution. Since we want to cancel liters of solution, we put that in the denominator. And then we have 0.550 moles of potassium chloride, and we will put that in the numerator. Now we would like to get to mass, which would be in grams, and in order to do that, we are going to need the molar mass. Putting the weight of potassium and chlorine in the calculator gives us 74.55 grams per mole. We now are going to include that in the equation, putting moles of potassium chloride in the denominator, and in the numerator we put the molar mass. Carrying out this calculation in the calculator, and this gives us a mass of 103 grams of potassium chloride. Now let's take a look at the next problem. In this problem, we would like to find the molarity of a solution which has a given mass of sodium nitrate. To find the molarity, we need 2 pieces of information: the moles of sodium nitrate and the volume of the solution in liters. as with the potassium chloride, we want to start by finding its molar mass, since we are given the number of grams, and we would like to convert grams to moles. So, using the calculator, we determine that the molar mass of sodium nitrate is 85.00 grams per mole. And we can now figure out this first part by simply converting 0.185 grams of sodium nitrate to moles using the molar mass. So we want to cancel out grams of sodium nitrate, and we put that in the denominator. And so now we've found enough information to give us the moles of sodium nitrate. Our calculation tells us that we have here 2.18 times 10 to the minus 3 moles of sodium nitrate, our solute. So now that we've found the value we need for the numerator, we need to find our value for the denominator. We are given 40 milliliters as the volume, but we need to convert that to liters. This is a relatively simple matter. We know that there's 1,000 milliliters in a liter. And so we simply perform a unit conversion and find that we have 0.04000 liters of the solution. We don't want to drop any significant digits. And now to find the molarity, we simply take the moles, which I've written here in blue, and divide it by the volume, which I've written in red. So 2.18 times 10 to the minus 3 moles of sodium nitrate divided by the volume of 0.04000 liters. And this gives me a molarity of 0.0544 moles per liter, and I can abbreviate moles per liter with capital M. Another way in which we can measure concentrations is to use various percents. I'm going to start off with what's called the volume percent. And essentially what the volume percent is, it is the volume of a liquid solute over the total volume of all parts of the solution. Since this will necessarily be less than 1, we have to multiply by 100% to convert it into a percentage. And then we use this symbol here, percent V over V, to show that the type of percent we are measuring is by volume. So if we were to try to put this in words, if we were to see a 15% volume by volume methanol solution, what that means is that there are 15 milliliters of methanol for every 100 milliliters of the total solution. If we wanted to know the amount of water, that would be what's left over, assuming that it's only methanol and water in the solution. So that would be 85 milliliters of water for every 100 milliliters of solution. The weight volume percent uses a slightly different kind of a calculation. What it's telling us is the mass of the solute in grams for every 100 milliliters of the solution. And we use this symbol here, W over V. Sometimes you'll also see this with M over V, using mass over volume, and it essentially means the same thing. To work with these, it's critically important that you understand what they mean in words. So let's do another example here. So let's say we had a 15% weight to volume sugar solution, That tells me that there are 15 grams of sugar for every 100 milliliters of the solution. So you'll notice the denominator in one of these percents is always every 100 milliliters of solution. Let's go ahead and look at some calculations which make use of these. So the first calculation I want to look at will deal with a volume percent, and the second calculation is a weight to volume percent. Again, let's go ahead and look at our notes view so that we can work out this problem. So in this first problem, we would like to find the percent of volume to volume, which we can write as percent V over V. And you'll recall that the definition of this was the volume of the solute over the volume of the solution multiplied by 100%. So in looking at the problem here, we have to identify the solute. So the solute is the methanol. And so it's going to be our numerator. And then we want the volume of the total solution, and that is 250 milliliters. Finally, we multiply this by 100%. And in the calculator, this gives us a value of 16.0%. Notice we have to tack on that extra zero to keep 3 significant digits. It's very important to understand how to interpret this in words. So if we were to write this out in words, what this would tell me is for every 100 milliliters of this solution, it contains 16 milliliters of the solute. Methanol. Let's go ahead and take a look at the next question, which involves weight volume percents instead. And in this case, you are given the weight volume percent. Let's also translate this to words. So in words, this is telling me that every 100 milliliters of this solution contains 22.0 grams of our solute, which is sodium chloride. So now we can use the weight percent as a conversion factor to go from the volume of the solution to the grams of the solute. So we write down our volume, which was given, 35.0 milliliters of the solution, and we want to cancel out the volume of the solution. And using our word form, we saw that for every 100 milliliters of the solution, that would be equivalent to having 22.0 grams of sodium chloride. Putting this into the calculator gives us a value of 7.70 grams of sodium chloride for those 35 milliliters of solution. Equivalents are useful for keeping track of the charge in a solution. And so it's going to be ultimately used here when we divide this by volume as another concentration unit. So the way we find the number of equivalents of any ion that we have in the solution, and I want to emphasize that, an ion, or in the case of something which is not charged, we would just say the compound itself. And we find that by multiplying the absolute value of the charge of the ion by the number of moles that we have in the solution. And when I say absolute charge, that just means that we take the charge as if it's a positive value, even if it is negative. You just convert the number to a positive number. So this is kind of confusing, I think, without looking at an example. So let's say we have an example here. So let's say we have 2 moles of sodium ions. The charge of sodium is 1, specifically positive 1, and the absolute value of 1 is just 1. So the number of equivalents would be 2.0 times 1, so that would be 2 equivalents. On the other hand, what if we had nitride ions? Nitride ions have a charge of 3 minus. Now we only care about the number, not the sign. So the absolute charge is 3. So to find the number of equivalents, it would be 2.0 times 3, or 6 equivalents. Ultimately, there's going to have to be the same number of equivalents of positive charge as negative charge in a solution. When we look at lab results, they are commonly reported in milliequivalents per liter for certain compounds that are present in blood or urine or other bodily fluids. So because they're going to be in much smaller amounts than equivalents, we'll usually talk about these in milliequivalents instead. So an equivalent is simply 1,000 milliequivalents. So what we want to be able to do here is translate these concepts to words. So if we see that we have a solution that has 150 milliequivalents per liter of potassium, what that means is that there are 0.150 moles of potassium ions in a liter of the solution. On the other hand, if we looked at calcium, calcium has a 2 plus charge. So if we said that there was 200 milliequivalents per liter of calcium ions, then this contains 0.1 moles of calcium ions per liter, because this value is multiplied by 2 to get you the equivalence. Now going back and forth between molarity and milliequivalents might initially seem a little bit tricky, but there's a rather simple formulation that we can do for doing this. So let's say that we're given the molarity of an ion, and we want to find its concentration in milliequivalents per liter. Getting from one to the other is simple. You simply multiply the molarity by 1,000 times the charge of the ion. On the other hand, if you want to go from milliequivalents per liter to molarity, you just do the opposite. You divide by the product of 1,000 times the charge of the ion. So if we look at a couple examples here, if I know that sodium ion has a molarity of 0.040, sodium has a positive 1 charge, so we multiply this by 1,000 times 1. 1,000 times 1 is just 1,000. So 0.040 times 1,000 is 40 milliequivalents per liter of sodium. On the other hand, if we're dealing with calcium, calcium has a 2 plus charge. So if we want to go from molarity to milliequivalents per liter, we multiply by 2,000, 1,000 times 2. And that would give you 20 milliequivalents per liter. If we wanted to go the other way, So if I wanted to go from 40 milliequivalents per liter to molarity, I just divide by 1,000 times 1. So 40 divided by 1,000 would be 0.040. On the other hand, if I want to go from 20 milliequivalents per liter of calcium to molarity, I take that and divide it by 1,000 times 2, because it's a 2 plus charge. So I'm dividing by 2,000. So 20 divided by 2,000 is 0.010 molar calcium. So we often see these, as I had mentioned, on lab test results, and we sometimes see milliequivalent per liter values reported on IV bags. So we'd like to have a better understanding of what those values mean. And so here let's do a simple example. I would like to find in a 1 liter IV bag that has 15 grams of magnesium chloride in it, I'd like to find what the concentration of each of those ions is in milliequivalents per liter. Since the question says we want the concentration of each ion, we're going to need to break that into 2 separate problems. One for the magnesium ion and one for the chloride ion. Again, let's go to our notes view. So let's begin by finding the molarity of these solutions. So we're given 1 liter as the volume, and we're also given 15 grams. We want to be able to convert that to moles. So there are 94.91 grams per mole of magnesium chloride using values from the periodic table. So the molarity, as we've defined it before, is simply going to be the moles of the solute, which in this case is magnesium chloride, for every 1 liter of solution. And since this solution only has 1 liter in it, that's going to make this a rather easy conversion. So we want to first convert the mass of the magnesium chloride to moles. So we put 94.91 grams of magnesium chloride in the denominator, and we know that that's 1 mole. Putting this in the calculator gives me a value of 0.158 moles, and since it's in 1 liter, the molarity is 0.158 molar. Now when we look at magnesium chloride, when it dissolves in water, it's going to separate out into 1 magnesium ion, but 2 chloride ions, because the formula clearly indicates that there are 2 chloride ions present. So first, let me find the molarity of the magnesium ion. And so I use square brackets to indicate that I'm talking about molarity. That's all that means. So the molarity of the magnesium ion is simply the molarity of the compound times 1, since there's only 1 magnesium ion in the solution. For chloride, though, it's going to be 2 times the molarity, and that's because there are 2 chloride ions for every 1 magnesium chloride. So putting that into the calculator gives me a value of 0.316 molar, which is twice as much as the magnesium. Now let's go ahead and find the concentration of both magnesium ions and chloride ions in milliequivalents per liter. Let's start with the magnesium. So to convert molarity to milliequivalents per liter, we just take the molarity and multiply it by 1,000 times the charge of the ion. And the charge of magnesium is 2. So this gives me a value of 316 milliequivalents per liter. For chloride, on the other hand, I'm going to take the molarity of 0.316, and I'm multiplying that by the absolute value of the charge, which is 1, not -1. Milliequivalents per liter are always positive numbers. And so we multiply that by 1,000 times 1, and that gives us what is a value that's not too surprising of 316. And so we see that the concentration of the milliequivalents per liter of the positive ions, the cations, is exactly the same as that for the anions, which is the result we expected.